they are what they need to be, and we're only going to be working with ideal gases in this module, just as a side note. Okay, so now that we know how a gas behaves ideally, let's learn a few more things that relate to these ideal gases, okay? So the next thing we're going to talk about is Dalton's law, okay? So Dalton's law of partial pressure, it states that when you have two or more ideal gases, so instead of just one gas, now we're talking about two or more, several gases mixed together, okay? The total pressure of the mixture is equal to the sum of the pressures of the individual gases. So all that's saying is when you have pressure, the total pressure, if I have a partial pressure, so let's say I have this one gas, a second gas, a third gas, like carbon dioxide, water, a couple different gases mixed together in a container. All this is saying is if you add the pressures of each individual gas, that's what you get for the total pressure, okay? So what this really is saying is that it tells us that the pressure of a gas doesn't depend on the identity at all of what the gas is. It only depends on the quantity, okay? So if I have water, let's say I have oxygen and hydrogen, okay? The pressure doesn't matter what's in it, okay? It just depends on what the volume is, how much of it you have, okay? So for instance, if I have, let's say I have a container, I don't have a top. So let's say I have a container here and a container here, okay? And I think they give you the example of 5 atmospheres, I think. So if you had 5 atmospheres of pressure here and 5 atmospheres of pressure here, okay? Well, if I put all the gas into one, okay, now I would have 10 atmospheres in here, total pressure, okay? So it didn't matter what it was, which gas it was. The only thing that really matters is how much of it you have, the quantity, okay? So that's really important. Now, in relation to this, we're going to onto the side, we're going to talk about vapor pressure, okay? So let's say I have my glass of water here sitting on the table, and I let it sit out for a couple weeks, however long, okay? Depending on how humid it is outside, what time of the year it is, okay? Let's say I set it out, and after some amount of time, eventually my water is going to be gone, assuming nobody drank out of it, okay? So what happened to that? Well, you know that it evaporated over time, right? That's what water does. It evaporates. Okay, so we were talking about water vapor pressure, okay? So I have my water, and we know it evaporates, but it wasn't boiling, because we know when it boils, that's when we get the water vapor, right? So if the water isn't boiling, how come it goes from a liquid to a gas, okay? Now, think back about how molecules move, okay? I've got water molecules in here, okay? It's a liquid. And remember, when a solid, the molecules they're vibrating back and forth, but they're solid, they can't really move around. Now, when we've got a liquid, they're moving around quite a bit more, okay? And every once in a while, molecules move enough to where they're moving fast enough, they have enough energy, where they hit the surface and they're actually able to escape through the surface of the water, okay? So eventually, all those molecules are going to hit the surface enough and they're going to escape, okay? They're going to have enough energy to do that. So it doesn't have to boil. Well, when that happens, that molecule has turned into a gas, it had enough energy to turn into a gas. And there's actually what we call vapor, that there's a certain amount of pressure that it's going to sit on the top of the water right there, and it's going to exert a certain pressure. So vapor pressure is just the pressure exerted by the vapor, which sits on top of any liquid. Okay, so now it depends on what the liquid is, which should make sense, right? If you have gasoline, let's say you spill a little bit of gas, if you're putting gas in a lawnmower, well, what happens is, does there stay a puddle very long? No. So the vapor pressure of gasoline has a large vapor pressure. So it's going to evaporate really quickly. That puddle is going to go away really fast. And you'll find that water actually has a really low vapor pressure. So it really depends on the vapor pressure of the liquid itself. If you look at the table 12.1, this shows you the vapor pressure of water, and it should make sense. It changes depending on the temperature, right? As you increase the temperature of water on a stove, it's going to be more prone to turn into a vapor, right? The higher the temperature goes, the more it's prone to turn into a gas. That makes sense. That's what we do when we boil water, okay? So the vapor pressure of any liquid actually increases with increased temperature. So we're going to be using this this list, so keep it handy. A lot of times we're going to give you a temperature of a liquid, and you're going to need that to be able to have the pressure of it, okay? So really think about this. The boiling point of a liquid is really just the point at which the vapor pressure is equal to the normal atmospheric pressure of 1, right? The second it's equal to the pressure, it becomes a gas, okay? The pressure is the same. So boiling point and the vapor pressure point of the surrounding atmosphere is the same thing, okay? So that's why if you are at a lower altitude, water boils more quickly because the pressure is lower. So it doesn't take as much heat to get to the same equal pressure as that outside atmosphere. So that's why. All right. What else was I going to tell you? So you can use this if you know the temperature of something. You can use that list to find out the pressure. So it's really nice. All right. Keep in mind one thing that you need to know is a lot of times scientists are, in order to get a gas, are using something else to go with it. So a lot of times it's water. So if you hear the words collecting gas over water or collecting gas in the presence of water, they want you to realize that the gas that you're collecting is probably also going to have water vapor in it. So it's not just going to be one gas, it's going to be at least 2 gases. So think about that for a second. When we did baking soda and vinegar, I don't remember if we did this last year or this year, and we caught it in a balloon, the gas that formed when we caught it in the balloon. Keep in mind, there was water in there as well, and so you're going to get some other gases in there. So that's when Dalton's law comes into play, okay? So let's look at the examples. It says, a chemist produces hydrogen gas in an experiment and collects that gas in the presence of water. If the total pressure of gas collected was 1.115 atmosphere and the temperature was 26 degrees Celsius, what was the pressure of the hydrogen gas collected? So, if we use Dalton's law, we know the pressure total is equal to the pressure of the hydrogen and the pressure of the water, H2O, water vapor, okay? So, they gave us the total pressure of the gas collected. So they give us the total pressure. So I'm just gonna plug that in. Did they give that yet? I'm gonna hold off on that. So first we're gonna use the temperature. They gave us a temperature of 26 degrees Celsius for the water. So we're gonna use our table. Flip back the page and go to the list. It says 26, and then if you look at the vapor pressure, it says 25.2 torr. 25.2 torr. So that's the pressure of the water, okay? It's in torr. And they gave us a pressure in atmospheres. So we need to make those match, okay? So let's go ahead and let's change this to atmosphere, okay? So I have 25.2 torr, and we're just gonna use our equations right here. So we know torr needs to go down here, atmosphere up here, okay? So we know that 1 atmosphere is equal to 760.0 torr, okay? So if I do that, I end up with 0.0332, atmosphere, because these cancel, okay? So this was for the water pressure of the H2O. All right, so now I have a total pressure they gave me, and I've got this pressure, which is good because this is what we're looking for, okay? So if this is what I'm solving for, I know I'm going to be subtracting my H2O over here, okay? So, it's okay. So let's take our pressure total, which was 1.115 atmosphere. And I know I need to subtract the one that I just found, which was 0.0332 atmosphere, okay? If I do that, I'm gonna get the hydrogen. Okay, so if I subtract it, I end up with 1.082 atmospheres. So hopefully if I did it right, I can add these back up. This is a partial for each gas, water vapor, hydrogen and water vapor, and I should get the total if I did it correctly. Okay, so go ahead and do on your own number 4. It's just like this. You're going to be using the partial pressures to add up to the total. All right, so now that you've done that, we're going to talk about another way to know what concentration is. So the last couple modules, we've heard the word concentration, okay? The first module was molarity, okay? And we said capital M, molarity, is a way to use for concentration. Now, the next module, I think it was 11 last time, we talked about molality, another concentration unit, okay? I'm not going to put the equations up. We've already dealt with them. We're going to talk about a third equation, okay? This is another way to know what concentration of something is. It's called the mole fraction, okay? So we are going to say capital X. This is another form of concentration, okay? So I'm going to give this to you. The mole fraction is simply just moles of part over moles, number of moles of the whole, okay? So let's go ahead and just do an example of this. I'm going to go ahead and get rid of that. Oops. Don't need to get rid of that. So we are on page 399 right now. It says a mixture of gases contains 3 moles of oxygen gas, 5 moles of nitrogen, and 1 mole of neon. What is the mole fraction for each component in the mixture? All right, so I need to look for a fraction for each. So I'm going to say, okay, X is the mole fraction, and I'm going to list each one so that I can keep track of it. Okay, oxygen is going to be O2. The next one they gave me was nitrogen, so I'm going to say N2. I'm going to go ahead and get rid of this because I've already got it right over there. And then the next one was neon, Ne, okay? So all this fraction is moles of the part, which is oxygen, over moles of the whole. So they gave us 3 moles, 3.0 moles of oxygen. They said 5 moles of nitrogen and 1 mole of neon, okay? So they gave us those numbers, those are the parts. Now, all we have to do is find the total. We can do that by just adding 3 and 5 and 1 gives us 9. So we have 9.0 moles, okay? I'm going to do that. It's just a fraction. It's the total, so it goes on the bottom of each of these, okay? So this should make sense. Your moles unit cancels, so you're left with just a number, just a digit, okay? So if I do that, and right here I end up with 0.33. Right here I get 0.56. And here I get 0.11. So this mole fraction is really just telling you how many parts of oxygen make up the part of the whole gas. That makes sense, right? If you have this many moles of oxygen over the total, that makes sense. So really a third of this is oxygen, and half, slightly more than half, is going to be nitrogen, and just about 1/10 is going to be the neon. Okay?